We're not the first to do this. It's actually been very useful. So let me start by telling you a little bit about multi-party number in hand. I guess that most people here, when they hear multi-party communication, they think about number on four-head communication, which is this model that's very useful for proving circuit lower bounds. For me, the motivation for thinking about number in hand, where each player has their own input, comes from distributed computing, which is my background. So think of a system with many, many participants. Each participant can only sense a small part of the environment, or maybe each participant is a server in a server farm and it gets some small chunk of data, and we want them to do something together. So obviously they're going to communicate in order to do that. These, by the way, are the kilobots from Harvard. So what is a multi-party communication protocol in this context? We're going to have k players, and they each receive a private input, which only they know. And the goal is for them to compute some joint function of their inputs. And there's two models you can think of for communication. Actually, there's more than two. But in general, like one basic design decision you have to make is, do they communicate by broadcast? Or do they communicate by unicast? So broadcast means that when one player says something, everyone receives this. And this is nothing else than the classical shared blackboard model. And another equally interesting setting for distributed communication is message passing, where I have the ability to send a private message to a participant if I want to do it. And then if I want to say something to two different players, I'm charged for that twice. But today I'm going to focus on shared blackboard communication, where I just am charged one time for putting my message out there, and then everyone can see it for free. And by the way, later on this week, Arkidev is going to talk about lower bounds for the message passing model. So this is also an active area of research. Why do we care? So in distributed computing, what we typically care about is how long is it going to take me to do what I want to do. So we want a lower bound on the number of rounds. This is different from what we care about in communication complexity, which is usually the total number of bits that you need to solve the problem. The reason we care more about rounds than we do about total bits is that a distributed system often has a very large bandwidth or capacity. We have so many participants that we can send a lot of bits in a very short time. The question is that enough for us to do what we want to do? So we care about rounds. And the way we model this is called the congest model. The way we introduce sort of communication complexity is we say in every round, every player is able to send some parameter b number of bits. And so the total bandwidth of the system is linear in the number of players, right? So this is very large. It's a very large bandwidth. If we are able to prove a superlinear lower bound on the total communication complexity of the task, then we get a non-trivial lower bound on the number of rounds. Take your communication complexity lower bound, slash it by b times k. That's the lower bound on the number of rounds. But we can't always do this. Sometimes there are problems which have a low communication complexity, but still there's something inherently sequential about them. So I'm not going to talk about that at all today, except at the very end. Today I will focus on proving communication complexity lower bounds and getting round lower bounds as a result.
What is n? K is the number of players?
Yeah, k is the number of players, n is the size of the input. And in many of the problems that we care about, actually k equals n. Your input is maybe the communication graph or something that you can see from the environment, and it roughly corresponds to the number of players. So think of these as being more or less the same. The exception to this is when we talk about things like MapReduce or very large data farm kind of problems, and there the size of the input is going to be much, much larger than the number of participants. Okay, but for that kind of problem, broadcast is not appropriate. You don't have servers that can broadcast a message to every other server. More problems? Okay, so having said that, I'm not going to talk anymore about the congest model. I am going to talk just about shared blackboard, the classical communication complexity model, and we'll have a lower bound that is powerful enough. It is superlinear, and so we will be able to get the round lower bound that we want. Just an aside, Strong lower bounds in multi-party number and hand communication have only started appearing in maybe the last 5 years. So what have we, the distributed computing community, been doing before then? The answer is, like a lot of other fields in theory, we're able to get a lot of mileage out of just reductions from two-party communication complexity. And usually the way that you do that, you take your system, which is some communication network, you divide it into two logical parts, and you do this in such a way that the cut connecting them is sparse. So you can't have a lot of communication going across quickly. And then you embed some two-party communication problem. You have Alice and Bob. Each one represents one side of the network, and you argue, well, if this distributed network is doing whatever I want it to do, then it's solving some communication complexity problem. And then you're able to say, we need a lot of communication. It's going across a sparse cut, so that's going to take a long time. And we have some really beautiful lower bounds that work along these lines. The problem is, what happens if your system doesn't have these sparse cuts? And the system actually that I'm talking about today, Shared Blackboard, is a very good example of this. No matter which way you try to slice it, it has no sparse cuts. So this kind of approach is not going to get you anywhere. So you really have to talk about the multi-party, the real thing that's going on here. All right, so the problem I'll talk about today is, of course, set disjointness, because what else? This is set disjointness. For the multiplayer setup, we're going to have k input sets, and we're asking, is there anything that all these sets have in common or not? I want to mention that there is no promise here. There's a version of this that's been studied before, which does have a promise, and it has applications in streaming. But this is something different. And it's convenient to think of this in the following way. The disjointness problem with n elements and k players is just the disjunction on all the elements. Is it true that all the players got this element? And we'll use this representation to sort of construct our lower bound. OK. Let me just give you one example showing why set disjointness is such a useful problem. So here's an example. Let's say I want to show that computing the diameter of a graph, which I get as input, is hard. So the way I'm getting these inputs is I have my k players, and each one gets some subset of the edges in the graph with possible duplication of edges. And what I want them to do is look at the union of all the edges that they got and tell me what is the diameter of the graph induced. So I want to claim that if I can compute the diameter of a graph with small communication, then I can solve disjointness. And we'll get the lower bound from that. The domain that we'll be reducing for disjointness is just the set of all possible edges, all unordered pairs AB. And here's the reduction. Suppose I get these sets as inputs for disjointness. We're going to construct in our heads a graph where each player takes the input edges that it got, and it puts in the graph exactly those edges that it did not get in its input. Okay, and all the players do this. Why did we do that? Right, and then we can just go and compute the diameter of this. The input sets are disjoint if and only if for every edge there is some player that is missing this edge. And this player in this reduction is going to put that edge in the graph. Okay, so in this reduction, the sets are disjoint if and only if every edge is put in by some player, which exactly means that the graph we're constructing is going to be a clique, and it will have diameter 1. Okay, if there is some edge in the intersection, nobody's going to put it in the graph, and it's going to be missing, and then the diameter will be at least 2. So that's an easy reduction. In general, a lot of these reductions are this easy. But I hope I've convinced you that set disjointness is a nice problem to think about. All right, so what can we say about the communication complexity of disjointness? We have k players, and each one gets n bits of input, so it's trivial that you can do this in order kn bits of communication. Just write everything. But it's also easy to see that you can do better. And one way to do that is the first player is going to go first, and it will write on the board all the elements that it doesn't have. Okay, so these are definitely not in the intersection. Player 1 didn't get them. Now we're going to move on to the second player, and it's going to add the elements that it doesn't have. But we're not going to write anything more than once, because we're conserving on communication. And we keep going like this until we've covered all the players, or all the coordinates appear on the board. If all the coordinates appear on the board, then there is no intersection because we've ruled everything out. And if we've finished all the players and there's something that doesn't appear on the board, then everyone got it. So the sets are not disjoint. What's the cost of this? Well, every coordinate is written on the board at most once. And in addition, it could be that some players don't have anything new to say, and they're just going to say move on. So that's another bit. So the total cost is n log n plus k. Much better than n times k. But in fact, you can do slightly better than even this by packing together the coordinates a little bit more cleverly. The way you do this is basically you notice, so let's say that we've executed the protocol up to some point, and there's some number of coordinates, z, which we haven't ruled out yet. So these are the coordinates that conceivably might be in the intersection. So notice that if the sets are disjoint, then every coordinate can be ruled out by some player. Right? Every coordinate is missing from someone's input, and that means that there is some player that can rule out a lot of coordinates in one shot. Right? Total of z is missing, every coordinate is missing from one player, then some player is missing at least z over k coordinates. The way we'll be a little bit more efficient is just encode these as a batch. Encode these as a subset of size z over k from the z that are missing, and then you get an amortized cost of log k per coordinate that you just ruled out. So the more efficient protocol basically goes through all the players. If you don't have a lot to say, you say nothing, you just say move on. If you are able to rule out a lot of coordinates at once, then you write them as a batch. And if we've gone through all the players once around and nobody had this many coordinates to contribute, then we are finished. We know that the sets are not disjoint. So this protocol gets us n log k plus k. And at this point, we asked ourselves, all right, can we do better? We know that sometimes these logs, even though they seem like they should be there, you can actually get rid of them by being clever. And my favorite example of this is, of course, Hastad-Wigilson. So if you think about just two players, sparse set disjointness, if I'm going to promise you that every player gets exactly s elements, you might think that the right answer is s log n. Every player needs to write these s coordinates, and it's going to take you log n bits to encode each coordinate. But they have this really elegant randomized protocol which actually gets you order s. So this log, even though it might seem inherent, it's not. Can we do something like that here? And I want to remind you that in our case, this log k is the difference between getting a lower bound and not getting a lower bound, because we need a superlinear lower bound. So n log k will, in the end, give you a lower bound of log k on the number of rounds, while n gives you nothing. So actually, we prove that you cannot get rid of it. We show that the information cost of disjointness is at least n log k. The plus k you get very, very easily. And this actually makes a lot of sense. If you think about it, what is this log k doing? It's pointing to some player. This is the identity of a player. So what our lower bound shows is that for every one of the coordinates, you must become convinced of the identity of a player who is missing this coordinate. You must convince yourself that it's not in the intersection because some particular player j didn't get it. And our lower bound is very explicit about this. The proof outline follows sort of the standard information complexity lower bound scheme. So remember that disjointness is a disjunction over conjunctions. The way we prove the lower bound is first we use actually an existing direct sum result, which says the cost of disjointness is going to be n times the cost of solving this little and in here. And then we just have to go and prove that and is not completely trivial, that solving and is going to take log k bits of communication. So I've been saying information, and I haven't said what kind of information I mean. The kind of information I mean is called conditional information cost. This is the notion introduced by Bar Yosef J. Ram Kumar and Srinivasan in 2004. And this is the definition. So we take a distribution that looks like this. This is my input x. And I also have an auxiliary variable D. And I'm going to analyze what an external observer learns from the transcript of the protocol about the inputs of the players, conditioned on this auxiliary variable D, which is actually really going to be important here. But just notice first that if I'm able to prove a lower bound on this, then this is, of course, bounded by the entropy of the transcript, so we get a communication lower bound. It's good enough, even though it's a little weird. And the direct sum that they showed is exactly what we need in this context, with some conditions which we'll have to satisfy. So we get that if you're working with the distribution mu on a single coordinate, take the product on n coordinates, disjointness is going to be n times as hard as solving and. And here are the conditions. First of all, the reason we need this auxiliary variable, you better make sure that the inputs are independent conditioned on it. So this is a constraint we're going to have to keep in mind. The other constraint is that the support of the distribution we're working with had better not include any inputs for which the and is 1. And this may seem strange, because if I know that the answer is 0, then this looks like a very easy distribution, right? But the answer is, actually, we're looking at not distributional cost, but worst case cost. So I'm taking a protocol which needs to be correct with high probability on every input, even inputs that are not in the support. And we're just analyzing it with respect to this distribution, which has this funny property. And this is very important in order for the direct sum to go through. In general, this looks like external information. External information does not obey direct sum. Only internal information does. So it's this funny trick that lets us argue by direct sum. OK, so I won't go through this. I just thought it might be nice for those of you who haven't seen it. But this is not new. It's just a sketch of the direct sum proof. But take my word that it works. What is new for our paper is analyzing the cost of and. So first, let me tell you what is the hard distribution. So let's keep in mind what we have to satisfy. First off, we have to make sure we're never going to get an answer of 1. That's because we need this for the direct sum. So to satisfy this constraint, what we're going to do is always pick some random player, z, and give it a 0. By doing this, we ensure that the answer is 0. What else? In general, we don't want there to be a lot of zeros, because if there's many zeros, it's easy to find one. So that would be making life easy for the protocol. We want to not have it find zeros. But we do need some zeros, right? Because all our analysis is going to be conditional in this auxiliary variable. We're already saying, look, player z got a 0. We want to make sure that we're left with entropy to get the lower bound. So this is how much entropy we're going to need, because this is the lower bound that we're proving.
Can you specify what exactly you're trying to show? Because if you know that your output is 0, so what are you trying to lower bound?
So this is what I said before. Let me go back to the definition. I'm taking a protocol pi which has good worst case error. On any input, it's going to give you the right answer with probability, let's say, 2/3. Okay, and then I am analyzing it with respect to a distribution that doesn't include some inputs. Okay.
Only for analysis.
Yes, exactly. I'm analyzing the information cost of this protocol with respect to this distribution, but I have to assume that it works on the all one input. Otherwise, I get no lower bound from this. Yeah. So the lower bound I'm proving here is not distributional. It's worst case. All right, so we said we need some zeros. We want as few zeros as possible, other than this one guy that we already gave a 0 to. Ideally, you would just pick one other player and give it 0, and then everyone else gets 1. But this fails the other criterion. This wouldn't be independent condition on the special player that got a 0. But this is easy to emulate. Just instead of doing this, give each player, other than the special player, give them zeros independently with probability 1/k. What we get is that the expected number of zeros other than player z will be 1. You really should take this to be k-1, but whatever. So we're emulating this, and now we get that the inputs are independent, condition on Z. All right. So now this is what we show, that if you take this hard distribution, and let's say you have a protocol with small worst-case error, then the transcript of the protocol needs to leak log k bits of information, even conditioned on the special player who got 0. So implicitly what I want to argue is that the transcript of this protocol has to reveal, it has to point to a player whose input was 0. And in general, I'm going to have two such players. One of them is going to be the special player Z. One of them will be one of the other players. If I can say the transcript always outs one of them, then half the time it's not going to be Z, it's going to be the other player. And then we're going to leak log k bits of information. Okay, so how do I formalize this idea of pointing? What does it mean that the transcript exposed the player that got a 0? There's actually a nice way to formalize this concept. So I'm going to look at what happens to the posterior probability that this player got a 0 after seeing the transcript. And we're going to show that often it happens that for some player I, we now believe that it got a 0 with constant probability, let's say probability 1/2, after I showed you the transcript. Whereas before I showed you the transcript, I really didn't think that this particular player got 0, because the prior probability was just 1/k. Okay, so the posterior probability is much, much higher than the prior. And this is where the log k bits of information are going to come from. So let me skip this slightly more technical way of saying what I just said right now. For those of you who are familiar, the log k comes in because the KL divergence between a Bernoulli random variable with constant probability of being 0 and Bernoulli 1/k is exactly log k. So revealing the identity of a player who got 0 is worth log k bits of information. Okay, so that's it. This is the way we get this lower bound. After doing this, we noticed something interesting, I think. We noticed that actually external information for shared blackboard is incompressible. We know that for two players, if I give you a protocol and it doesn't reveal a lot of information to an external observer about the input, then you can compress this protocol really, really well to something that's roughly the external information that it revealed and some polylogarithmic factors in the communication. And actually what we get here is that the gap is much bigger as the number of players increases. So notice that what is the information cost of AND? How many bits am I revealing when I solve AND? I claim that I never need to reveal more than this log k bits of information, no matter what the distribution is. And this is easy to see. I'm just going to have a protocol where I go through the players and they tell me their inputs until I find a player that got a 0, and then I stop. What's the entropy of the transcript? I can compress it to just the identity of the first player where I stopped, right? So it's just log k bits of information, and that's also an upper bound on the information revealed. So computing AND is cheap in terms of information. But what is it in terms of communication? It's expensive. And this is very easy to see. So if I take a distribution where with probability 1/2 everyone gets 1, and with probability 1/2 I'm just going to hide 1 0 somewhere, it's easy to see that to solve AND on this distribution, you need to find this player who got a 0. You need to essentially go through a linear number of players until you're convinced that there is no such player. So we get a gap of k over log k. Okay, and this is not the most convincing example in the world because it's a small example. The input size is 1 bit per player. Maybe this doesn't scale.
What exactly your model? Like, who is speaking at round I?
So this is actually very important for our model. We go with the usual shared blackboard model, which says that the next player to speak is a function of what's written on the board. Okay, so you look at the board, and based on that, we need to know who goes next. You could think of other ways to define it, sort of like the more adaptive models of communication that are used in adversarial coding. If you do that, you won't get this big a gap, but you still are going to get a gap very likely. So this is an interesting thing to think about. Okay, so I just wanted to say that we're working now on generalizing this to something that actually does scale with the input, and the answer seems to be that it's roughly k, with maybe some polylogarithmic factors. Okay, let me also mention, without saying much about, we know that for 2 players, internal information is the amortized cost of solving many copies of one problem. As the number of copies goes to infinity, the communication for solving all of these together, the per copy cost is just going to be exactly the internal information, what the players learn about each other. What is the situation for shared blackboard? We don't exactly know. We were able to show that the compression part of this, so the less equal here, does go through. You can compress to the external information cost. But we know that that's not tight. So actually, you can sometimes compress to better than the external information cost. So there needs to be some intermediate definition. For reasons that I don't have time to get into, you can't just take the 2-player internal information cost and generalize it the way you would want to. And we're trying now to figure out, skip all of this, what is the right notion? What should we write here in order to have this be tight? Which in some sense is asking what is the right analog for Shannon's entropy for one-way communication, for internal information, for interactive communication. How should you generalize this to the multi-party shared blackboard setting? All right, so let me conclude here.
Are there any questions?